Hello everybody, my name is Anastasia and I will be a moderator for this webinar. Today our speaker is Dr. Erik Deumens, who will tell us about progress in their work on algorithms for large-scale computing. So Erik, please.
Thank you. So I will be talking about the work that we've been doing in the last several years to try and really simplify programming very, very complex algorithms like the algorithms that we are encountering in very complex electronic structure, correlated electronic structures theories, and to execute them on modern architectures. And we know that the modern architectures of computers are also becoming more and more complicated. So we are facing two challenges. One is we want to get more accuracy. In order to get more accuracy in our models, we need to go to more complicated theories. And we are having to use computers that are more complicated because they have multiple processing units, multiple cores in each CPU, and then there are heterogeneous ones. There are some that are regular CPUs, and then you have GPUs. And what I'm going to talk about is one approach to try and simplify programming such complicated architectures. And this is work in progress. We think it's pretty exciting, but it's not completely done yet. And the work has been done over the last several years as an outgrowth of the research done at the University of Florida under Dr. Bartlett's leadership since the 1980s. He has been developing a computer code called Advanced Concepts for Electronic Structure, ACES, and then in 1990 there was an ACES 2, and in 2006 we released ACES 3. And for ACES 3 we have enrolled Professor Beverly Sanders, who you can see is one of our co-authors. She's a computer scientist with a specialty in parallel programming, and so we've been using some more modern computer science concepts to develop this new work. Nakul Jindan is a graduate student who is working on his PhD, and basically the work that I'll be reporting that we did in the last 2 years is a lot of the work that he has been doing. And then Victor Lotrick is a postdoc who is our wizard programmer. So my talk will have 3 pieces. One is the computational problem, then how do we basically design software to attack this computational problem, and then at the very end, or the third part of the talk, I will specialize and show how adding in GPUs, which is something that we did in the last 2 years, works with that software architecture. So this community already knows, of course, what computational chemistry is, and today, like Anna says, it's a great day because we got the Nobel Prize for computational methods, and that's a very nice recognition of all the work that we've been doing, and it also points to the promise and the expectation of society to deliver on that promise of what computational methods can do. And so we want to create software and make sure that that software is sufficiently flexible to meet new needs, sustain developments without having to be redesigned every 2 years when a new computer system comes out, and also can be designed in such a way that it uses this new architecture as much as possible, because there's a lot of power theoretically available in all those new massive computers, but it's not hard to get. It's not like it used to be 20 years ago where you could just recompile and you would have faster code. And when you're trying to deal with very accurate electronic structure calculations, there are multiple problems. For one, you have to deal with a large amount of data. And if you're doing a CCSD calculation for about 100 electrons, you have to anticipate that there need to be 2 to 10 arrays that are about 80 gigabytes big, and there is probably one array of 800 gigabytes. And you just need to make sure that that's managed somewhere in the proper way. So you need to be aware of that as a design. And given the modern computers and the typical size of computer cores and nodes and RAM and disk, it's these first arrays that you probably will put in distributed memory on a parallel computer. And then the second array is often too big, and you either recompute it. That's actually the modern way to do it, because storing them on disk, because the disk speeds have not grown as fast as processor speeds, may be slow. But that doesn't always, it's not always the case. And so one of the things that we need to learn as a community is that there may be multiple ways to attack a particular problem, and it may not be completely clear in advance when you're writing the code that a particular way of doing things is the best way for every problem that any user may want to do with that code. And that will lead to part of the design that we put in our software development, that is to try and postpone certain algorithmic decisions as long as possible and actually only make them at runtime. So when you're making a design for software, you need to make a trade-off between the computation effort, the memory usage, and the communication. And with communication, I include communication to the disk arrays and disk storage systems. And this is just, you're not supposed to really read this, you're just supposed to be impressed. Everybody in the audience, I'm sure, has at some point looked at the CCSD expressions, and if you write them down in any programming language, it looks like a total mess. And this should be, at this point, an incentive for us to think, well, we don't want to actually code this. We need to find some way to tell the computer to write a program to execute expressions like this, because if we are going to write lots of expressions like this, and some of them even more complicated, then we're going to be making mistakes, and we'll be spending months and years trying to find the errors in our mistakes, and it's very counterproductive to try and do it. So this is really something that humans should not look at, and only computers should deal with. That should be part of the design. So what is our approach to try and deal with the complexity of the software and the algorithms that we want to code, and the complexity of the computers that we want to run these complex algorithms on? And our philosophy is to bring in an abstraction, and the abstraction we call the super instruction architecture. And why do we think of a super instruction? Well, a basic computer for many, many decades, from the very beginning that computers were built, have instructions that operate on a set of numbers. Typically they are stored in register, and then you produce so for instance, an addition. You take two numbers and you produce a third number. Our concept is that we want to use the same way of thinking, but basically supersize the idea. And instead of having the computer work on a single floating point number of 64 bits and then do something with another single floating point number, also 64 bits, and produce a third, we want to work on a block. And this is an idea that many people have used, but many people have used it as a design principle for their program, and then they still write the program in terms of the individual elements in the blocks. And we wanted to design an architecture and a way of thinking that treats the blocks as the lowest atomic level, and you cannot look any lower except by using some really special instructions to sort of go do something on the side. Very similar to if you write a program in C or in Fortran, you basically operate on floating point numbers, and 99.999 of all your operations should be floating point operations. And maybe every now and then there may be a bit level operation. And then you do something special, and you know that if you call the routine or the operation to do something at the bit level, it's going to be very slow. But that's not a problem as long as there aren't too many of them. And we want to do the same thing. We want to think in terms of blocks. And we call a super instruction an instruction that takes a block, takes another block, does a complicated operation, and produces a third block. And then when we need a block from memory, we get a block from memory, we write a block from memory. We never do anything with an individual number. And then the program gets written in terms of super instruction assembly language. And we sort of try to draw the analogy with, in the old days when people wrote assembler, they basically said you take first instruction, load a block or a number into register A, load another one in register B, do the addition operation, store the number from C into memory location X. And so we want to think in terms of that level, but now with blocks. The advantage of blocks is that even with modern processors, if you take a typical block, and we have some experimental evidence from doing the runs, that the blocks that we're dealing with are actually quite large. We think in terms, when you're thinking of a couple cluster calculation and you want to create the new T2 amplitudes, there are several diagrams, the ones that take the most computation, where you have to do a contraction of integrals with the old T2 amplitudes over two indices, and you produce an estimate for the next T2 amplitudes. So there, if you now do your integrals and your T2 amplitudes, if you do them in blocks, these blocks are four-dimensional blocks. And the size of each edge of a block, it turns out it's somewhere between 25, 30, 35 numbers. So you are talking about a block of number that is 30 times 30 times 30 times 30, 30 to the fourth. So now you're talking about 10,000 to 100,000 floating point numbers in one block. And that one gets contracted with another block of the same size to produce a third block that is also the same size. So now even the fastest processors will take multiple seconds and sometimes minutes to really compute, to really carry out this super instruction. And this is our great advantage, because now if I do my scheduling of the instructions a little bit smart, then I could say I'm going to issue an instruction that will operate on two blocks that are already present in memory. So this processor is going to be busy. In the meantime, I have made a request for the next block that I know I'm going to need in the next super instruction to come from some remote location. And the time that it takes to finish that ongoing super instruction is large enough for even a very remote location to deliver that block. And so the next super instruction finishes, the new super instruction gets issued, and the new super instruction needs to check whether all the required blocks are present, and yes, the blocks are all present, and it can immediately proceed. So by thinking and working in terms of super instructions, we have a natural way to hide all the communication behind computation. And that actually turns out to be very beneficial. And it also makes for a lot of flexibility and execution efficiencies. So when we look at this diagram, we write the super instruction assembly language, and then we have something called the super instruction processor executing and reading the language and executing it. We actually have a compiler in between. We write the super instruction assembly language, and I will show you examples a little bit later. It looks like very simplified Fortran or C, or it's a relatively simple language with some simple parallel constructions. And the super instruction processor is sort of like the Java virtual machine. It reads bytecode. Our compiler generates bytecode, and then the super instruction processor reads the bytecode and executes all the instructions. And what actually happens is when there is a super instruction that says do a contraction over these two indices of one four-dimensional block with another four-dimensional block producing a third four-dimensional block, what happens is a subroutine gets called, which is one of the typical subroutines that all quantum chemistry codes now have, that just do these contractions. And at some point we translate that into a dgem, and basically we execute a dgem. And if we have multiple processors in the CPU, then multiple processors can be engaged in that computation. But the assumption is that once you call one of these super instructions, that subroutine does not do any more communication. It has the assumption that all the data that we'll ever need are present in local RAM. So the super instruction processor basically consists of an interpreter, and then it issues these super instructions, which are computational kernels, and they are by definition and construction always localized on a single node. They don't do any data sharing or locking. Everything has to be prepared so that once the kernel is running, it starts to work, and it has no more impediment, no more waiting needs to happen. So let me talk about the instruction a little bit more in detail. So in the traditional programming language, the unit of data is a floating point number, and the operations consist of combining floating point numbers. And then we need to figure out as programmers how to get all these operations and data pipelined and vectorized so that we get good performance. In SIAL, what we try to do is we try to elevate the programmer's view of the problem to a higher level, where the unit of data is a block, which we then use in our language. We call it a super number of floating point numbers. So it's a block of floating point numbers, and the instruction is then a super instruction, which will take a long time, and there the assumption is that there's no communication. And each of the kernels are just written in any programming language that you like. If you like Fortran, or if you have the code already in Fortran, the only thing you need to do is sort of change the header of the subroutine so that the data is properly interpreted, but the body of the code can be reused. And we can write it in Fortran and in C or in CUDA or whatever. And these are the code that do the little chunks of work. And then at the SIAL level, the super instruction assembly level, is where the programmer expresses the flow of the algorithm in a general way. And so that has one of the great advantage of SIAL is that it becomes very simple, because when you declare an array, you declare the array by stating its block-like nature, and you do not have to specify the details of the blocking. That is actually left all the way up to runtime. So in the program, you never have to specify that the blocking of the array. Suppose you have a calculation that has 1,000 basis functions. You never have to specify that all loops over basis functions are going to be divided up in small subloops, because that is done at the runtime. So as a programmer, you just have to know that it's done in chunks, but you don't know exactly what the chunk is. You never have to worry about making sure that your beginning index is the correct one. That's all taken care of by the processor. So the way I like to describe this is as at a very high level. At the top you see this program CCSD is written in SIAL, and it basically calls multiple routines, and they can be in different languages, and they will take care of the details of the computation, but they do not have to worry about synchronization with other kernels or other CPUs, because that's all done at the high level of SIAL. And so, to summarize, the SIAL program gets translated by the compiler into bytecode, and the SIP, the super instruction processor, executes the bytecode, and essentially when a bytecode is translated as a particular instruction, it gets translated to the name of a subroutine. That's a compute kernel, and it executes kernel number 1 or kernel number 2 or whichever one is appropriate in the flow of the program. So if you then want to find out, well, how is the parallelism visible in this architecture of software? So at a very high level, you think of every node, every participating node is executing the SIAL program, or the SIP is executing on every node, and it is reading the SIAL program, and it reads the whole SIAL program, and it just figures out some piece of it that it's supposed to do. The SIP itself is a program that's written in C and C++ and some Fortran, but we're now creating a new version that'll be purely in C. And the reason we do that is because we want it to be a program where computer scientists are very comfortable so that they can help us optimize the performance. And the chemists, they just write the super instruction code, and that can be done in Fortran or C or CUDA or whatever they want, or it can be generated by some code generator like the tensor contraction engine or any other way. And the SIP is a program that uses MPI and also OpenMP inside the node, but the main the main way of communicating over distributed memory systems is using MPI. So to quickly go over what does this do, if we look at the mathematical expression of one of the CCSD terms, we see here a contraction of V is the integrals, 2 electron integrals in the atomic basis, and the T amplitudes are the old amplitudes, and you're trying to generate the next iteration for your amplitudes and call them R. So what we want to do is we introduced the concept of also a super index, right? So that's why the whole language is supersized. And the super index, if you have a basis of 1,000 functions, then you divide up that range of 1,000, say, in 100 segments of 10. Or it could be a different number, and that you don't really know what it is, but you know it's something like that, and just to fix the ideas, let's say that it's 10. And then you basically have the capital indices M, N, I, and J. They go from 1 to 100. And then each M is just one segment of a range of basis functions, and the little mu, nu, I, J are the ones that go over the orbitals inside each segment. And those are the ones that are made invisible at the SIAL programmer level, and they're only visible inside the compute kernels that are the super instructions. And so instead of writing this first line, the green line, which has the extra loop, in SIAL we just implicitly make the contraction over all the orbitals that are common to the segments L and S. So you're summing over L and S, that's the contraction over super indices L and S, and the star operator between V and T is a super instruction that basically contracts over all the orbitals inside segment L between V and T and segment S. And then of course in this particular case that gets very quickly and easily translated into a dgem call, which then is executed. So the super instruction are basically computational kernels that get executed on a single CPU, and they assume that there are no communications going on. And by having that architecture and assumption, it was very easy for us when GPUs became much more available than when we started this design in 2003. And so 2 years ago, we basically said, oh, now we have all these GPUs available. The architecture allows very much to really make optimal use of one GPU or many GPUs, because the GPUs have exactly this kind of constraint where for using a GPU efficiently, you need to specify a well-defined compute kernel. You need to make sure that all the data that's necessary for the computation expressed in that compute kernel is present on the GPU. So you have to sort of manage the communication in advance and send the data there, and then you issue the instruction for the compute kernel to be executed, and then it'll do it very fast and it produces the result. And if you can save data between subsequently called super instructions or compute kernels, then you want to keep the data on the GPU instead of moving it off and moving it back on. And all those thoughts are exactly what we have been doing with the SIAL programming model and the super instruction architecture, and so it fits very well. The only thing that we had to do was that instead of having kernels written in Fortran or C and C++, which we had been doing before, we now have to add CUDA kernels, which of course is not a big deal. And then some of them are built in because, like, many of the contractions are general and we know everybody's going to use them, so we program them once and then they're available for everybody else. But if you want to do something special for some of the very advanced methods, then you may want to create your own super instruction to do something special to one or two blocks in order to contract them into a third block, or maybe the contraction is not a standard contraction, or maybe it's a little bit more complicated operation, and then you can write a super instruction on your own and optimize it for whatever purpose you want. So how does the SIP work? The SIP basically has a master who controls what everybody does. There's a set of worker nodes, and they also are owners of the distributed arrays. So every worker has some memory that is just some scratch memory in its RAM, but it also has ownership of a couple of blocks of the arrays. And so if one worker needs a particular block, there is a standard algorithm, very simple, assigned in advance, where every node can compute where the block that it needs is residing, and so they can issue a message directly to that node that owns the block and say, please send me this node, send me this block. And then there is another set of nodes, they're called the I/O nodes, and they handle what we call served arrays, and they are essentially disk-backed arrays. And the way the disk-backed arrays work is that the memory of the I/O server nodes is used as a cache. And so workers can store blocks in particular nodes, and then as long as these blocks are being called up by other workers a lot, they stay in memory and they are very fast for accessing. But if they are not needed, then they sort of get written to the disk, and that allows us to run on a smaller number of workers problems that require a very large amount of data and still make sure that the performance is good by using that caching. And then we use standard techniques that are used all over the industry for optimizing cache use. And then what the workers do is they basically have a table of instructions that are the byte codes, and these byte codes translate to super instruction compute kernels that are basically subroutines, and they go through it. They make sure that all the arguments as blocks are present, are available, and then they issue the instruction to go and execute on these arguments, and the arguments are most of the time blocks. Every now and then there are some instructions that take as one of the arguments a single number, but that's very rare. Most of them are all super instructions. The advantage of having this very coarse-grained execution is that since every super instruction, once it's issued, the processor is working in this subroutine for quite a long time. And the short time between the execution of two super instructions can be done to do a lot of bookkeeping without really slowing down the whole program. And that gives us the advantage of making sure that we keep track of performance data for every run. And so when we do an execution, at the very end we get a little performance report, whether we turn performance on or not, because the overhead is minimal, it's negligible. And that means that we can always see, oh, we did the calculation and it took a little longer than we expected. Or when you look at the inspection, you can say, hey, there was this one loop that had a lot of wait time. So maybe we should look at that loop and rearrange it a little bit so that some of the data gets fetched first before we do the execution, or rearrange the order in which we do things, because our performance numbers at the end will tell us where the execution was very efficient and where the execution had a lot of waiting. And that comes essentially at no extra cost. So we don't have to put extra performance things in to get performance measurements and then run the calculation again. And that's an advantage, especially when you're trying to run very complicated problems that require 1,000 CPUs, run for multiple hours, and then you say, ooh, there's a performance problem, now we have to run it again. We don't have to do that. We just run it, and then we have the performance numbers at the end, and we say, hey, there was a performance problem. Let's look at the detailed performance log, and we can probably find out what's going on with that. And the SIP is something that the chemist who implements the complex algorithms of, say, couple cluster theory don't have to worry about. This is the domain of the computer scientists, and they will make sure that it runs fast. And as a chemist, you don't have to worry about it. They just do their job. So the SIP also handles the distribution of the data, which is the data access in computational chemistry algorithms is very irregular, as we all know, because you're trying to correlate basically every electron with every other electron, and there are multiple theories trying to improve upon that, but basically it's very irregular, and that's what we are trying to address a little bit by having a very flexible memory layout, and by not requiring the programmer to really explicitly state anything about how memory is laid out. We give some choices as to, well, this array is a local array, then you can assume that every block that is a member of the array is present in local RAM. It's a distributed array. That means that every block is distributed among a set of workers, and it's going to take some time to get an arbitrary block. If the block is locally present, then you get it immediately. That's a benefit, but you should count on the fact that it'll take some communication to get to that block. And then the third kind of an array is a served array, which means that it's stored on a bunch of nodes, and if the cache flow is very good, then you get it very quick. If the cache flow is not optimal for your particular problem or for a particular loop, then you may have to wait a little longer because you may need to get the data back from the disk. And that is sort of the very coarse-grained level that the programmer should think of. And it's the SIP programmers who will then make sure that everything gets optimized. But the chemistry programmer doesn't have to think about more details about where the data lives. They just say this, I want something that's very fast, then you make it local. If you want something intermediate, you make it a distributed array. If it's a very big array, then you have to make it a served array. And then all blocks are automatically cached wherever possible. So one of the advantages of using the super instruction architecture that we have found is that it increases the programmer productivity incredibly much, because what you can do is you can come up with an algorithm that you write down mathematically, and you write it very easily in SIAL. You don't have to worry about all the little ownership of who owns a block and what is the sub-range of one index. Everything is automatically blocked for you. The SIP does it at runtime, and the user who actually runs it can still change it at the event of running. And so the programmer can write things, and a whole class of mistakes that are little tiny mistakes when you try to send all these MPI messages, making sure that the message doesn't come into a deadlock and that you're sending the message when you're ready to be sent. All that's taken care of the SIP, and it's not visible in SIAL at all. So the programmer just has to focus on the algorithm and make sure that you get the correct sequence of operations. And then you get good parallel performance, because by having these blocks and by changing the blocks, we can sort of tune the performance on a whole range of machines. And over the past decade, since we started this work in 2003, the generation of computers has changed quite a bit. The processors have become a little bit faster, and switches, communication interconnects, have become very different in performance, and the architecture of nodes and memory banks has changed, and we've always been able, with very little effort, to make sure that we get really good performance on any platform, sometimes only by tweaking the size of the blocks. And since the code is fundamentally written block oriented and block focused, that's the main thing that we need to change to create a different balance between the compute speed of the processor and the communication speed and latency and bandwidth of the interconnect. And so that has been very beneficial for us. And by having the SIP keep track of the statistics of how data is moving and how fast it moves, we get this nice report that is, of course, not very interesting to the chemist, but it's very interesting to the computer scientist who is writing on the SIP and trying to optimize the SIP as a parallel program. And so that has also been very useful in improving our code over the years. So now I want to quickly show what SIAL looks like. And this is one loop, and you can see here there's a pardo, and one of the things that you will notice is there are no ranges on these indices M, N, I, and J. And that is because when you declare an array, you basically, it's implied, the SIP who looks at the SIAL code already has read the input program, the input data set, and it knows what molecule you're trying to deal with. It knows how many atoms there are. It knows how many basis functions there are. It knows what basis functions there are and which ones are the s orbitals and which ones are the p orbitals. It knows all that stuff. And it also knows how you want these indices to be blocked. So if it knows that there are 1,000 basis functions, it knows that you want to do your basis functions in chunks of 10, and so you don't have to specify that as a programmer. And you can just say pardo over these indices, whatever their ranges are, and of course you as a programmer sort of know what it is, but you're not going to type any mistakes because you don't have to type it. And then here you have a temporary array, and these are very simple. They can just be used, and at the end they will go away. And then you have a parallel loop. Pardo is the outer loop, and then you just have a normal sequential loop over L and S, which is the contraction. And you see here the sequence of the operation. You get a block from wherever it may live. You then execute compute integrals, which is a super instruction that will produce the block V. And then you contract, that's a second super instruction, you contract V with T, you create temp, and then you add the contribution from temp in the temp sum. And that's basically it. And then at the very end, you at the end of the serial loop over LNS, you basically have the result, which was our previous formula, and you put that wherever it belongs. And that's it. And then at the end there is a SIP barrier that basically says, okay, all the processors, all 10,000 of them may have been working on this, and at the very end they need to all wait till everybody's done with this section before they go on to the next section of the code. So that works out very well. So here I just indicated the Pardue loop. And here we request the block, we do the contraction, we put the result, we're done. So here the promise of GPUs, of course, is now that we have the same thinking that GPUs require already built into our programming style, and that is in the last year we now basically made some relatively small changes to the whole code and architecture, and now we can run using 1,000 GPUs if there are 1,000 GPUs available. We actually tried two things which confirmed what everybody else has learned, but that's how we learned it ourselves as well, and it was a good warm-up. So the first thing was to try and make the use of GPU completely invisible to the programmer of SIAL. And that meant that we basically, inside each super instruction, had to make the decision, if a GPU is available, we copy the blocks to the GPU, do the computation, and copy the result back to the host. And it turns out, as you can expect, there were a few sections of code where this actually works. Like here, you can do this. We can execute this on the GPU. The amount of computation that needs to be done on the GPU is quite big, so it is reasonable. But the motion of data in and out of the GPU still turned out to be too much. So the contractions by themselves were really good, but if we looked at a total CCSD calculation beginning to end, it didn't do enough, because the motion of data basically made us lose all the thing we gained from having GPUs. So that's when we did the second approach, which is also very similar to what many other people are doing at a normal programmer level, which is we put in some directives to tell the compiler that we're going to do multiple things with the same amount of data, and you can move it to the GPU once and then leave it there, because there are going to be a couple of instructions coming. And the directives are added to our SIAL language, and of course they're very, very similar to what other OpenCL and other open accelerator proposals are for communicating with accelerators. So we turn the GPU on, we turn the GPU off, we load data, a block into the GPU, we unload it back, we allocate a block for work on the GPU to keep some data, and at the end we can free it. So now the code is a little bit more complicated, because we have to put these green instructions, and for the rest everything stays the same, but we have to tell the SIP what we want to do here, what we expect. And so now I'm going to give a simple example. We do perturbative triples, which of course is the one that works very well. That was the first result we got. And you can see that when we're using 500 processors and 500 GPUs, we get a speed up of about a factor of 4, which is very good, and it's very similar to what other codes are having, and so we're pretty pleased. But we're now working on some improvements to try and see how can we improve this, because we don't really want to make all these. We would like to have this more automatic, and so that's the next step, and that's also Nakul's thesis, to try and make this more automatic, because the annotation is not trivial. I mean, it still requires work. You have to go look at the code, and we would like it to be automatic. So what we have done is we've created a sophisticated performance model that is based on these analysis that comes out. And so what we do is we first make a dry run. We go through the code and sort of figure out how much memory is going to be used, and that will allow us to optimize the distribution of memory allocation for temporary blocks and for long-term blocks on each of the nodes, thereby minimizing the motion of data if we can. At the same time, we also make an estimate of how long does it take each sequence of super instructions to execute, and how long does it take for a whole Pardue loop. And then with that, we essentially rewrite the SIAL code. And then, so the programmer writes a SIAL code that is logically correct, and then the next step is to run this performance tool on that code, and it will rewrite, reorganize some loops, bunch some loops together, split others out, and then allocate them to different numbers of processors, such that at the end everybody runs at and meets the finish line at the same time. And these implementations are going to be built in what we'll call ACES 4, because it's going to be it's a significant rewrite, and we found that it was easier to rewrite it than to try and change the old code. So the way this works is we basically want to do work scheduling. And so we define something called a work item, and a work item can be one or more Pardue loop structures with a bunch of super instructions inside. And then we want to distribute all these work items to all the workers we have. And when you're only talking about a small number of workers, range from 1 to 1,000, then we found this is not that important. But if you really want to go to the new Titan or Blue Water scale, where you want to run 10,000 cores or 100,000 cores, then it becomes very important to really look at the different pieces of work and estimate and calculate how long is each one going to take, and distribute it over the right number of workers so that the total execution time comes out meaningful. So you have to set up all the information with your input data, then you run the performance model, like I said, and then you generate a new SIAL program that takes into account how the work is going to be executed, and it will basically assign some work to a specific set of workers. So if you have 100,000 workers, you're going to say, well, these diagrams, for instance, one of the ladder diagram, we're going to do that by the first 5,000 workers. But then there are all these other little ones. We're going to assign 10 workers to do this diagram and 50 workers to that diagram, and then we come up with a schedule that sort of looks like this. So you have a bunch of workers from W1 to Wn, and there's a work element, E1, and that gets allocated to a bunch of workers, say 4, and it takes a little bit of time. And then there's another element, E4 that gets done by the 2 CPUs on worker 5 and worker 6. That's a typo. And then worker 7 happens to be a GPU, where we have a particular GPU work that we estimate properly, taking into account the data movement to it and the amount of performance that it has. And then so this whole performance model comes up with a diagram like that, trying to make sure that at the very end that all the work gets done, and that all the workers are as busy as possible, and that there are very little blocks that say idle. And of course, in my little diagram, it's overly simplified, but that's the way it works. And so far, we've had some test runs going, and it actually does seem to work very well. And this process is completely automatic. So in some sense, it is an automatic optimizing compiler. It takes the initial SIAL, uses the performance model, and the performance model is run for the specific calculation that you're going to do, because you're assuming that it's going to be a big calculation, a huge chemical system with a large basis set, large complicated calculation, and you take into account the architecture of the system. How many GPUs does it have? How many cores does it have? How much RAM per core? And then it goes and it makes this estimate, and it produces a slightly rearranged SIAL program that still is logically correct and the same, and then it'll execute in this optimal way. And that's basically what I wanted to say. I want to thank these organizations for funding, and I'll answer any questions.
Mm-hmm. Thanks, Erik. Now, if anybody has questions, please type them into the webinar window that you see in your program. And meanwhile, let's take questions from offline audience, if there are any.
Yeah, I have a question right away. Hi, Erik, again. Very impressive, very interesting. Now, can you comment, we just had a meeting with computer scientists on a related project where we talked about communications and optimizing code for different architectures. And they were insisting that we should give up on having local disks at all. They were saying that this architecture is dead, and all new machines that are going to be available, large-scale machines, will be essentially diskless. As far as local nodes are concerned, there could be some, shared disk, but communication with disk will be through network, and as such, we cannot, hope on using it. And your code is still using some disk space, right, to keep your arrays.
Yes, it is, but it's not local disk. It is using a global shared disk. So basically, we assume that all the nodes have local RAM. We assume that all nodes are connected by some fast interconnect, like on the Cray would be the C star, or on a regular cluster it would be an InfiniBand interconnect of some kind. And then that there is some large long-term storage outside, which could be a Lustre parallel file system or something. We do not assume that the nodes have local disks, and actually we've never tried to use local disks. And I agree with the computer scientists that is sort of going away, because it becomes very expensive, and also from a power point of view, to have these local disks run, and they are hard to maintain. They're going to fail, and then when they fail, you have to do maintenance on the node much more frequent than you would be necessary. Whereas the global storage systems, like the Lustre parallel file system, can be built in such a way that you can do maintenance and replace broken disks without taking the file system down, right? Because you can build in the complex RAID structure and whatever. So I agree with their assessment, and we don't use local disks.
How much of input-output do you have, and how efficient it is using this remote storage?
The input-output during the execution is very efficient, and it's very similar to a communication between the nodes, because what we need to do is we just need to communicate to these I/O nodes, and the I/O nodes then on most systems use the same interconnect to talk to the actual nodes that have the disks on them, and that depends on, like in Lustre, there are these OSS servers, and it's the same architecture for many systems, so that works very well. One of the things that we do have a performance problem with is the initial. If we want to do a restart and we want to dump the memory of all the nodes, or a section, we don't dump the entire memory, but there are some blocks that are capturing the state of the calculation, and we want to write that out to disk. That is a problem, and we are now looking at HDF interface to improve that, and using MPI/IO. to make that more efficient.
So the model, if I understand it correctly, is that you have this remote storage, you have some nodes that have fast access to it, and then they fetch data into memory, and then they pass the data through this fast switch between the nodes, right?
That's correct. That's correct.
And that's working, so that's I see.
And that works. That we find that works well.
All right, okay. Yeah, but indeed, yeah, restart is a big problem for our stuff because we have a lot of intermediate data. And,
Yes. So that we haven't completely solved yet.
Okay, very interesting. So more questions here? No? Let's see.
And there is one question from our online attendee about slide 20. What is the problem with Blue Gene? Yeah, you say that your code is transferable except for this special case. What is so special?
Yep. The problem with Blue Gene is that the I/O structure, the switch is this complex torus, and we have always in our assumption have sort of assumed that anybody can communicate almost equally well with anybody else. And for all of the switches that we've worked with, that has never been a problem. Except on Blue Gene, that does run into a problem, because there you have, if you take these nodes that are served arrays, on a Blue Gene architecture, for every compute node, so you have groups of nodes, and they come in groups of 64, and each 64 nodes has one I/O node that has a good access to the I/O subsystem. And we have not found a good way. We need to do some re-architecting. And if we would rearrange our parallel loops a little bit, then we know by hand, we know that we can get the Blue Gene to run. But the way the code is currently written, it doesn't run. And so this is why we're so eager to get this performance model working, because if we have the performance model working and the automatic code rewriting also working, then we will basically ask the automatic code rewriter to rewrite for the Blue Gene, which has a slightly different architecture for the switch and the way the communication flow, because the I/O nodes are sort of special. And we can build that into our model, and then the model will correct the code. So we've postponed really optimizing code for Blue Gene because we know how to do it by hand, but it would take a lot of effort. And we now are working on this automatic procedure, and we are confident that this automatic procedure will give the correct result. So the Blue Gene is a problem that is caused by its specific architecture, and we have a way to solve. It's a temporary problem. We think we can address it once we have this optimizing procedure in place.
Okay, so anyone else here or from
Well, I have kind of a not very important question. I'm just curious. So, you said that now we have ACS4, not ACS3, right? So, and
that's correct. We're working on. It's not available yet, but if you're interested, then we can give you access to the early code. But it's not really ready yet.
And it's really a major rewrite, you say, right?
Yep. It's a complete rewrite. I mean, the code is restructured, and one of the main reasons we had to rewrite it this much is we started with the nice principle in writing ACES3 to try and keep the chemistry and the computer science separate. But then because of the pressures of deadlines and funding and whatever, there was some entropy crept in, and now there is a lot of stuff that is really chemistry specific in the computer science part, and computer science specific stuff in the chemistry parts. And then if we ask a computer science graduate student to work on the code, then they get all sort of, it becomes, yeah, they get all confused by the weird things that happen. And so we are now trying to really make that very clean and clear, sort of start with a new slate and make sure that the computer science code is written the way computer scientists write code, and then when we engage a graduate student or a master student to temporarily work on our code, we can tell them very nicely, look, this is what you should do, and they will find the code familiar to work with according to the standards that they learned in software engineering classes. And so that's why we actually used it to do a code rewrite rather than just evolve the code.
All right. Okay. Interesting. I guess a lot of
to be able to use people more in their comfort zone rather than force them to learn.
Yeah, and chemists are never scared of computer science, I think so.
What's that?
And chemistry students are never scared of computer science, so I think it tells something about the culture. And
no, that's true. But it's not all the chemistry students. One of the things that I found is that the number of chemistry students who are really willing to write code is shrinking.
That's unfortunately true. Yeah, I agree with that.
And so we need to find new areas where we can get people who are willing to write code, and the computer science part is where it is. Like currently, now that we're doing GPU work, there are several students who are just interested in learning to do GPUs, and of course the principles of parallel programming are exactly the same, but working on something that is GPU and CUDA is exciting. And it's good on their CV, and so they're willing to work with us. Whereas if it was before just standard MPI, you know, it's sort of the same principles, but it wasn't as interesting.
Yeah, fashion is, you know, big thing. We all know that.
Yeah.
Marketing. Okay, very nice. So, do we have more questions?
No, there seems to be no questions anymore. So,
well,
thank you again,
thanks
Erik.
a lot. Great seminar, and we will, of course,
Well, thank you.
on the website, and I'm sure there will be some ongoing discussion based on what we learned today. Thank you.
Yep.